A train appears at the far end of the track. At first, it is only a shape in the distance. Then the horn sounds. As the train comes closer, the whistle seems sharper and higher. A few seconds later, the train passes, and the same sound suddenly drops lower. Nothing inside the horn has changed. The driver has not pressed a different button. The train has not changed its voice. So why does the sound change? The answer begins with the way sound travels. Sound is not a solid object moving through the air. It is a pattern of pressure waves. When a horn blows, it pushes and pulls the surrounding air, sending out a series of compressions. These pressure peaks move outward one after another like ripples spreading across water. If the horn is standing still, the wave crests spread out evenly in all directions. A listener nearby receives them at a steady rate. That rate is called frequency. A higher frequency means more wave crests arrive each second, and the sound is heard as a higher pitch. A lower frequency means fewer crests arrive each second, and the sound is heard as a lower pitch. But a moving train changes the spacing of those waves. When the train moves toward you, the horn sends out one wave crest, then another. But before the second crest is released, the train has already moved forward, so the next crest begins from a point slightly closer to you. The same thing happens again with the next crest, and the next. In front of the train, the wave crests become closer together. Their wavelength becomes shorter. Your ear receives more crests every second, so the pitch sounds higher. After the train passes, the situation reverses. The horn is still producing the same sound, but now it is moving away from you. Each new wave crest begins from a point slightly farther away than the last one. Behind the train, the crests spread farther apart. Their wavelength becomes longer. Your ear receives fewer crests every second, so the pitch sounds lower. This is the Doppler effect. It does not mean the horn itself is changing pitch. The source frequency remains the same. What changes is the frequency received by the observer. That distinction is important because the Doppler effect is not really about a sound deciding to rise or fall. It is about motion changing the arrival pattern of wave. A common explanation says that sound is compressed in front of the train and stretched behind it. That image is useful, but it can also be misleading. The air is not being squeezed like a solid spring along the whole track. The better explanation is that each wave crest starts from a new position because the source is moving. In front of the source, the crests start closer together. Behind the source, they start farther apart. Your ear translates that changed arrival rate into pitch. This is why the effect is easy to hear with a fast train, an ambulance siren, or a racing car. Their speed is large enough, compared with the speed of sound, that the change in wave spacing becomes noticeable. With a slow-moving person or a bicycle bell, the same principle still applies, but the shift is usually too small to hear clearly. The Doppler effect is not limited to sound. Light can show a similar shift. When a star moves toward Earth, its light can shift slightly toward the blue end of the spectrum. When a star moves away, its light can shift toward red. Astronomers use this effect to study the motion of stars and galaxies. Doctors use a related method in Doppler ultrasound. Reflected sound waves can reveal how fast blood is moving inside the body. Police radar uses the same basic idea. A wave is sent toward a moving car, reflects back, and returns with a frequency shift that contains information about speed. The train whistle is only the most familiar version of a much larger rule. Motion changes what an observer receives. A wave may leave its source with one rhythm, but movement changes how that rhythm arrives. So when a train rushes past and its horn drops from sharp to low, you are not hearing the machine change its note. You are hearing motion itself, written into sound.